before I begin, I'd like to thank the organizer and Cam for giving me this opportunity to present and for sharing some of his talk time with me. So I'm going to present the disk formation at high res from the AGORA project. So I only give a brief introduction to the AGORA project itself. It's nicely covered by the Jihoon and Ramon in earlier talks. So this is the Milky mass progenitors at high redshift. So from the 8 different numerical codes, but from the same initial condition. So we can see that some codes, in some codes we can see a nice and thin disk, while the others have much elongated or clumpy disk. So we are going to explore what's the formation channel of these galaxies. So these are mock RGB images, excuse me, generated by the radiative transfer code skirt. And we will use these mock images to identify the size and shape of the galaxies and compare it with the observational data. So we first investigate the time evolution of the various disk properties, like disk to total ratio, which is basically mass fraction of the disk stellar components, based on their kinematic decompositions. So we first noticed that all the participating codes reached disk dominated or exceeding the disk total ratio exceeding 0.5 at around res 3 to 4. So we also noticed that some codes, we only highlighted the 3 most extreme cases, but some codes showed a rapid spin-up or the rapid increase in disk total ratio, which coincide with the decrease in stellar half-mass radius and increase in inner stellar surface density. So this transition, the major merger at res 4, which I represented as a gray shade region, is responsible for this transition. So in this time, we present the size evolutions of the galaxy disk as a function of their stellar mass. So this time we can see that some codes shows a steady increase in their size. So left panel shows the stellar half-mass radius, and while the right panel shows the size of self-forming gas, which is a proxy of the cold gaseous disk. So we can see that these 3 codes shows a steady increase over time, while the other codes shows the distinct contraction phase followed by an expansion phase. So which is resemble the wet gas compactions reported in the earlier studies. So in this talk, we classified these AGORA codes into the 2 groups, whether they shows a clear signature of the wet compactions, which is these 5 codes, and the others, which shows little to no signature of wet gas compaction. So one of the main differences we found between these 2 code groups is the difference in the stellar age gradient. So this is the mean stellar age in each radial beam. So x-axis is the distance from the center in a disk plane, and y-axis is mean stellar age in each radial beam. And we separate the thin and thick disk to the spheroidal components based on their kinematic decomposition, and the spheroidal components, or the green squares, shows much older populations with flat or positive age gradients. And more interestingly, the thin disk components shows differing behavior between the 2 code groups. The codes with compaction, which I colored with the blue, shows the flat or positive age gradients even for the thin disk components, while the orange groups, or the codes with compactions, they shows the negative age gradients for their thin disk components. So to explain these behaviors, we trace each star back into the time where they initially formed and see whether they are moved either inward or outward after the formations. So the code without compactions, excuse me, with the blue codes, they shows the positive gradients due to the outward stellar migrations, which means that they move outward after the formations. This is due to the fact that they don't have a steep gravitational potential wear, and due to the turbulent nature of gas-rich disk, depending on the code. On the other side, on the other hand, the code with compactions shows the stable orbit after their formations, which means that they have little signature of the radial migration. This is due to the sufficiently high inner mass concentrations during the compaction, and this is the main driver of the negative edge gradient is the inside-out panching that shapes the former stars in inside-out manner. And still, it's important to highlight that all the codes in this AGORA project shows the relatively match well with the observed galaxies in terms of their size and shape. So the left panel shows the shape parameters at redshift 2.8 and their comparison with the observational constraint. And the right two panels shows the effective radius versus stellar mass and the comparison with the observed galaxies. So regardless of the onset of compactions, the two older galaxies are qualitatively match well with the observational data. However, this agreement is only achieved when we carefully incorporate the dust attenuations and dust extinctions. So for reference, the upper panel shows the MOG images with, MOG images without any gas medium or dust contents. So we can see that some codes in some codes the hot mass ellipsoid is biased to the inner dense core, while after the dust the incorporating the dust attenuations, their effective radius or hot light ellipsoid become much larger and reach out the values that align with the observed galaxies. So this is the conclusion slide. So we have studied the disk formation channel, and the wet compaction and subsequent inside-out canting is one of the main drivers for some codes in the AGORA galaxies, while the disk evolutionary channels without apparent compaction is also observed in the other set of codes. So thank you for listening to my talk.
Thanks. So we have time for questions.
Quick question. Did you show us, I didn't catch it, whether there's an overall end correlation between having a compaction and the radius of the disk today?
So we do have correlations that the codes with compaction have much smaller size in terms of their stellar hot mass radius. But that kind of difference is mitigated when we use the MOG images and when we observe the effective radius with the graphite using MOG images. Hot mass is different, much compact in their size.
So I may have missed it because I had to step out for a minute. But you didn't address at all why different codes, some codes give compaction, some don't? I mean,
yeah,
any ideas you want to speculate?
I discussed it in this draft, but so there's there's so much things that play a role. So some codes shows the codes with delayed cooling prescriptions tend to shows weaker signature of wet compaction, or some codes with gas rich. With more gas contents tend to have lesser degree of these kind of single compaction events. So
I guess in a bigger picture sort of view, this goes back to Ethan's point. So how are we as a community now going to decide which one is correct? And the answer cannot and should not and never shall be the one that best fits the data, right? So this.
we can talk more in the topic break.
Good topic.
Yeah.
Are there any other questions?
Thanks for your talk. So for those positive gradients, what's the reason? What drives their the stellar migration?
The codes without strong compactions have shallow gravitational potential wear because of the lack of the inner mass concentrations during the compactions, and they are more turbulent and gas rich and turbulent. So we think that it caused a main driver of the radial migration.
Thanks.
Okay, let's thank the speaker once again. And